Hello and welcome back to Functional Analysis. And first I want to thank all the nice people that support this channel on Steady or PayPal. This is the second part in our spectral theory and we will talk about examples. The overall assumption here is that we have a complex Banach space X and a bounded linear operator T. For this we defined the set sigma T, the so-called spectrum of T. Now you already know lambda is an element of sigma T if and only if T minus lambda identity is not invertible as a bounded operator. The first new thing I can tell you today is that usually we will omit the identity in our notation. One can ignore the identity here because everyone knows what it should actually mean and we save space every time we use this expression. And of course, when we talk about the spectrum, this operator here occurs a lot. Okay, then let's go immediately to our first example. A good start would be to look at a simple finite dimensional example. Therefore, our Banach space X is then given by Cn. And our linear operator T should act on any vector X, like the diagonal matrix with entries lambda 1, lambda 2 and so on the diagonal. In other words, the result of Tx is simply the vector lambda 1 x1 until lambda n xn. And here you see immediately that the set lambda 1 to lambda n is exactly our spectrum of T. Now please remember that we learned in the last video that in the finite dimensional case, all the points in the spectrum are eigenvalues. So the spectrum is equal to the so-called point spectrum. Indeed, in this simple case here, we can immediately write down the eigenvectors. They are just given by the standard basis in Cn. Okay, I think that's enough we can say in finite dimensions. The interesting things happen of course in an infinite dimensional case. For this let's choose the LP space. We've already proven that this is a Banach space for p between 1 and infinity. So here you should see this is a straightforward generalization of our Cn. The only difference is that the chosen vector x here does not have an end. Otherwise I want to have the operator T to do the same as before. Therefore we could write this as a one-sided infinite matrix. So you see, this is the overall idea to find a generalization of the finite dimensional example from above. But of course we really should state the formal definition of the operator T. So we take complex numbers lambda 1, lambda 2 and so on, with the property that they form a bounded set. And this can be stated that the supremum of the absolute values is finite. With this we then define T as a bounded linear operator from LP into LP, simply by setting the jth component of Tx as lambda j times xj. Of course this fits in with our definition from above, but now you see we need this condition to get a bounded operator. Okay, at this point you should see what we did in the finite dimensional example still works in this infinite dimensional example. In particular, we find simple eigenvectors such that all these values are eigenvalues. So let's immediately write that down. For example, E1, the sequence 1, 0, 0 and so on, is an eigenvector corresponding to the eigenvalue lambda 1. Of course, in the same way, we have E2 with 1 at the second position as an eigenvector with corresponding eigenvalue lambda 2. Hence you see, we continue this for all our lambdas. Therefore, we have shown now that all these lambdas lie in the spectrum of T. In other words, at least we have a subset relation here. On the other hand, we immediately see any other complex number can't be an eigenvalue of T. Therefore, this set is indeed the point spectrum of T. However, you already know, this is in general not the whole spectrum of T. Indeed, the important thing that could happen is that this set is actually infinite. And then it has an accumulation point, which is something that cannot happen in the finite dimensional case. Okay, then in the next step, let's consider such an accumulation point. So let mu be a complex number with the property that it is not in the set itself, but in the closure of the set. Okay, maybe an example is very helpful here. So it could happen that lambda j is given as 1 over j. Then the only possible accumulation point would be mu as 0. Hence, in this example, we would have our eigenvalues as 1 over j, so they tend to 0, but 0 itself is not an eigenvalue. In fact, this is the general result, t minus mu is always injective. Now at this point you might already guess, in the next step we want to show that this operator is not surjective. Now with this result we know that mu is in the spectrum of t as well. For showing this, let's use a proof by contradiction. Now assuming that the operator is surjective, then we know it's also bijective. Please remember, the injectivity was not a problem at all. Okay, and now we can use the famous bounded inverse theorem to conclude that the inverse of our operator is also bounded. Knowing this, let's try calculating the corresponding operator norm. At least we know this is greater or equal than the norm when we put in one of our ej's. Please recall, this is just a sequence with zeros, with the exception that at the jth position there is a 1. For this reason, the acting of the inverse operator is easy to calculate. We just get the inverse of the number lambda j minus mu. Also very simple is then calculating the p norm, we just get the absolute value of this number. Okay, and at this point you should see a problem here. This estimate we have shown holds for all natural numbers j. And that's a problem because we know with the lambdas we can get as close as we want to mu. In other words, the reciprocal here will explode. Or more formally, you can choose a subsequence of the natural numbers here and then this sequence goes to infinity. So no matter how we put it, this number here can't be finite. And that's the contradiction because we know it should be bounded. Therefore, our conclusion is it's not surjective. Okay, let's summarize what we have found. The spectrum of t contains our lambda values and also the accumulation points mu. Now it's not hard to show that these are indeed the only possibilities for the spectrum. So this is what the spectrum of the operator t looks like. The first part is the point spectrum of t, the eigenvalues, and the second part is the continuous spectrum together with the residual spectrum. In fact, later we will be able to show that for p less than infinity, the residual spectrum is indeed empty. Therefore, in our case, this is actually the continuous spectrum. Okay, I think that's good enough for this example today. Let's use the next videos to talk about general results about the spectrum. Therefore, I hope I see you there and have a nice day. Bye!